Welcome back to Mathematically Speaking. I'm your host, Adam Allred. In the last episode, we mentioned different cultures and their different calendars before the Gregorian calendar took over. But is the only difference between all of those different calendars that they chose a different point for year zero. Let's look at the Mayan calendar to investigate. The Mayan calendar was set as base 20. Now, whenever I mention base 20 or 60 or 10, think of a clock that ends at that number. Base 10 is what we in America use daily, pretty much around the world use daily. There are individual numbers 0 through 9, and then you start combining digits to make new numbers after that. So a counting system that is base 20, there are individual numbers 0 through 19, and they start combining differently at 20 onward. But why base 20? Well, that requires us to go back to the counting bones of last episode. Remember, some of them have scratches in groups of 29. Now it is speculated that it is counting an entire lunar cycle, but what else could they have been counting to mark their calendars? Well, if we look at Mayan culture, what around them could have given them reason for a base 20 counting system? It was super hot, so they could have gone with 10 fingers and 10 toes. But another possibility is that women's menstruation cycle roughly lasts 20 to 28 days. Now, as an aside, the cycle for a period having people is different across the board, so I'm using the numbers of a quote-unquote regular cycle. The markings on these counting bones were counting a lunar cycle, but the numbers that they got to define the lunar cycle could have been a menstruation cycle, giving the phrase menstruation created mathematics. If we look at the Spanish word for month, mes, it is similar to menstruación. Probably butchered that, and I'm terribly sorry. This would imply that women in charge of the calendars, making them the first mathematicians and the first astronomers. Now, the Mayan calendar consisted of two parts, the Tzolkin and the Hab. The Tzolkin was a 260-day calendar, which is close to the length of a human pregnancy, and was split into 13 groups of 20, and it was only used for rituals. The Hab was built into 18 months with 20 days each, which gives us the 360 days, and then 5 days of religious ceremony. Their calendar was better than the Gregorian calendar. Its approximation of the year was 365.2420 days. They based their approximations on the planet Venus, which is visible in the sky in the morning and in the evening. And in the last episode as well, we discussed how hours, minutes, and seconds were defined. In this counting system we use for time is in base 60, meaning that for numbers 0 to 59, there are individual numbers and you start counting them at 60, or combining them at 60. To do the math necessary, you can still use your hands, and I'm going to try to convey this over audio. Do your best to follow along. One hand is designated to be a 5 hand, just the 5 fingers. The other hand is designated as the 12 hand, and the 12 is made up of each of the 4 fingers and the 3 segments of each finger. So you would count groups of 12 if you were trading, and then keep track of how many groups you have with your 5 hand. So if I was going to give you 37 bananas, I would have 3 fingers on my 5 hand and 1 segment on my 12 hand. This idea of a base 60 allows to maximize counting on one hand, making it an easy decision for early hunters and gatherers, regardless of how many divisors the number 60 has or how many natural phenomena occur in base 60. Again, when we speak of arithmetic, it's a number that makes sense. Being able to count to 60 on both hands makes more sense than limiting yourself to 12. You can't count with your toes. That doesn't make sense. They aren't malleable in the same way fingers are. So having a hand designated for groups and a hand designated for individual units makes more sense. Now, from all of this, we have temporal counting, or counting of time. But obviously, ancient peoples needed more than just a calendar to build a society. You need to have an idea of spatial counting. You need to be able to build things. You need to understand how areas and volumes relate to the world around them, and the simplest of these is a rectangle. This would also be true of the rectangular prism, which is just a rectangular base that's been stretched out to give it height. The parallelogram, a rectangle with one corner pulled while the opposite corner is held down so that it slants to the left or right. Its area is also base times height, but more important than being able to calculate areas to know how many crops they had or how much crops they had. There's a critical idea in geometry called similarity. And it's that two things can have the same properties without being exactly the same size. This allows for scaling when building or surveying land. You can even have a drawing of what you wanted to build to scale, and since it was going to be similar to what you were going to actually build, any properties the model or the drawing had, the real thing would also have to have. But this would have been an obvious thing to them. It's prevalent in nature. And the understanding of similarity is seen in religious ornamentations and their construction. Now you may be thinking that, well, then this idea of geometric counting or spatial counting is just an extension of arithmetic. So arithmetic gave us geometry, and our skills of temporal counting were extended to that of space, which is how we have geometry. However, this apparent chain does not imply a foundation in arithmetic in the sense of a foundation of a house. Without it, the structure would crumble. Without arithmetic, there still could have been geometry, which we will see when we arrive in Greece, whose central mathematics was geometry. They didn't do arithmetic the way arithmetic was being done by Mesopotamia and Egypt. They were doing arithmetic via geometry. So it's possible that those things could have come first and then we had arithmetic. There's no foundation there. Now, as we continue on, subjects such as algebra will appear to be based on arithmetic or an extension, but this also does not imply foundation. Foundation of mathematics became the focus of the mathematical community in the 1800s, only to no avail. One of them was known as intuitionism. So far, we have discussed the basics of arithmetic and geometry, both of which just seem to appear by necessity. No proper study of mathematics has occurred yet, just astronomy and building human society. So how did this happen? Well, Immanuel Kant, a 17th century German philosopher who wrote on everything, came up with intuitionism. He lived a very reclusive life, never going more than 20 miles from his home, and he had the same routine every day. And there are stories of how you can tell the time based on when Kant would pass your house on his daily walks. In his concept of mathematical intuitionism is that the idea of temporal intuition, our ability to sense time, and spatial intuition, our body awareness and understanding of our three-dimensional world, led to the creation of arithmetic and geometry respectively. The mathematics exists in our head somehow, and we are just able to use what's already in there. This also implies that every mathematical subject must either be founded in arithmetic or geometry, or perhaps a combination of the two. This idea does not last long, though, as a major philosophy of mathematics, but there are still some today who hold it as the foundation of mathematics. However, there are still some today who hold it to be the foundation. This quick dismissal of Kant's idea is why today he's known as a philosopher and not a mathematician. Now, if you remember, the thesis of this show is that math is a human activity and affected by politics, economics, philosophy, and anything else around it, which means that it develops from the world around us as a better tool to understand it. It is not just something that is pursued academically. So can intuitionism fit into this? In a way, yes. The world around us is what develops our intuition. It is not a fixed thing that we are born with, so our intuition could just be the way that mathematics has shown itself, but it was developed by the world around us. But in another way, no. Kant's idea is that mathematics exists a priori or before knowledge. So if we lived in a math-free world, for Kant, it would still exist in our minds. The social perspective that this show is taking is that we invent math as we need it based on what is around us. This implies that the question that was left open last episode, where does number exist? Or what is number? The answer is that it's in our heads, our collective heads. The another question that's left open from the other position is that what put intuition there? For Kant, the answer would be God. But there is one more important implication to this theory, that the notation, the words that we use to convey place value, the grouping we choose, already exists in our head. That we as a collective species decided that this grouping is the one that is the best one to use. It wasn't by having a meeting and all voting. It wasn't democratic. It was by our actions. It was by how we measured things, by how we decided to demarcate time and distance. And even though there are two different methods of measurement in the world today, metric and imperial, those systems exist because we as a collective decided it. In the US, initially everyone was blue collar, so distance had to be something that those using it could make sense of. For example, a tailor. When they are measuring out their material, they will hold it at the center of their body and pull some out until their arm is straight. That's 1 yard of cloth. A yard is a tangible unit of measurement. So even though the imperial system has no continuity, with each unit of measurement representing something physically different, in the metric system, there was the desire to have everything uniform. This started after the French Revolution, who tried to make everything into groups of 10, including the calculator, the thing that took millennia to invent and create a consensus over. They somewhat succeeded with the metric system. Everything is 10 away from the next unit of measurement. It too had physical representations. The kilogram was actually just redefined. It used to be defined by a hunk of metal known as la grande K. It was secured safely in a series of glass bell jars outside of Paris. But this year, in 2019, at the Conference of Weights and Measurements, those in attendance, and I'm assuming a committee of some sort, redefined the kilogram to be defined by the Planck constant. The ampere, used for measuring electrical current, the Kelvin, used for temperature, and the mole, a unit for atomic mass, was also changed. And they changed these things from something physical in the world that we can touch to a universal constant. And for the most part, this will only affect those who are doing very complex and very precise measurements, but those very precise measurements are the most important. Most of us could still get away with using Lagrange K as a kilogram, as it is only off by 10 micrograms. And the original intent of the metric system was to make measuring available to everyone by making it an unchanging thing. The redefining the kilogram achieves that goal. I hope on this episode you realize the importance of measurement. And although simple, extremely crucial to the world as we know it, and it can only be done because we decide it to be. So what do you think? Let me know, and maybe I'll share your answer on the next episode. Thank you for listening. This has been Mathematically Speaking.